Okay, so we should start. Yeah. Okay, so this will start today with paragraph 2.3, which will be about a model for the P1 delta localization. So let me start by reminding you of what we have seen last time. So we last time proved the following theorem. So we start with M, a complex of pre-sheaves of O delta modules on the category of smooth foliation. And so there was actually a few variants of this. One of them was this. So the spectrum which you obtain by first taking the infinite suspension spectrum on M, and then apply to this some localization factor, namely making this P1 delta local, A1 local, and also local for the topology, CFT. Then this spectrum is stably, so it's an omega spectrum, so it's stably fibrant. So interesting in knowing that this is stably A1 et al. Or CFT. So this was one statement we have seen last time. In fact, we have seen actually that maybe I could try to say it here also. So yeah, so maybe as a remark or as also a reminder, we also have seen that this particular spectrum is associated to the omega less than 1 pre-module, which is the one obtained by applying this thing, this localization to M itself. So remember that if you have an omega less than 1 pre-module, you can associate to this a particular spectrum, which is actually given by the same pre-sheaf at each level. Okay, and so if this is this is N, then remember we have this N underline, which is, if I remember correctly, is given by maybe a shift of N. Okay, and so we know that this guy is actually given of this, is also of this shape. It's given by, it's a periodic spectrum in some sense, and each level it's given by the localization of M itself. Okay, so it's just to remind you of what you were doing last time. So this is this we have seen last time. So what I want to do today is the following. So today I want to try to understand concretely the functor or the P1 or the functor log P1 delta A1 CFT. Maybe I should say that I think in the last lecture I was writing this simply by log P1 delta. Okay, so now I want to put all these together just to stress that we are doing these three localization. Okay, is this clear? Last time it was only that thing here, but I said it maybe last time that actually I really mean the whole thing. And so today I want to write this down because there will be I will consider somehow variant of this where I would put only one of these three, I think. So I want to understand this functor. So in the sense that I want to have a model for it, which tell me what it does when I apply it to some spectrum like this. Because for the moment this is only obtained via the general machinery of boost field localization, which is very unexplicit in some sense. So we don't really have any nice model of these objects. And so what I want to do today is to try to see how, if this is possible, to write down some nice model for these complexes. Okay, and we will see actually that this is not really possible. And but I will try to explain how we can somehow get around this problem. So to start, I want to start by recalling some the classical situation of the A1 et al. Localization, just to give you an idea of what kind of thing we expect or we would like to have. So just a brief reminder on the A1 et al. Localization. So this is a classical story, which I could say it's at least a variant of it is already known in the paper of Morev-Vygotsky. Okay, so let me remind you about the following construction. So let's work over the category of smooth scheme over some base field base scheme S, and let's consider K a complex of free sheaves on this thing. And so I want to describe to you a model for the so-called A1 et al. Localization of K. Okay, so something which is a little bit concrete. Okay, so so for this we have the following construction, which is called the Suslin-Vygotsky construction, and it's denoted by Sing or maybe SG. So this is for singular A1 of K, and so I can write down the definition. This is by definition equal to the total complex associated to a simplicial complex, which is the simplicial complex that you obtain by taking internal homes with value in the algebraic simplices from algebraic simplices with values in K. Okay, so let's see where delta n, by definition, this is the spectrum of K T0 up to Tn, mod out by 1 minus T0 plus Tn equals 0. Okay, so there is this version of the algebraic of the topological simplex where we take defined like this. So these are called the algebraic simplices. So when we apply this functor home internal delta into K, what do we get? We get a simplicial object in the category of complexes of pre-sheaves on smooth varieties, and we can build from this a single complex by taking the total complexes. Okay, is this clear? I mean, if you have any doubt about anything, I can explain more. Okay. So this is called the Suslin-Vygotsky construction on K. And now that there is the following proposition, which gives an answer to the question having a model for the A1 eta localization. So the proposition says the following. Let's say K as before. Maybe so here we have to assume a few things. So we assume that S is Noetherian of dimension finite, and we assume that K is a complex presheaves of Q vector spaces. So there will be some problem with torsion, but so we assume these two conditions, and then the conclusion is that then if I apply the Suslin-Vogorsky construction to K made fibrant for the étale topology, so étale fibrant, then this is the A1 étale localization of K. And actually, maybe I should say it here also that when I say A1 étale localization, this actually means exactly the same as saying it's an A1 étale fibrant fibrant replacement. Which is actually a bit more correct, maybe, to say it like this. Okay. So, and I want to just recall quickly the proof, which is not so complicated, just to single out two important ingredients in this proof. So let me remind you also what does it mean to what does this statement mean really? So a statement, I mean, the way one recognizes that something is an A1 étale fibrant replacement is by checking two things. So we want to know that the map is an A1 étale local equivalence, and second, that this object is A1 étale fibrant. Right. So this is what we need to check. Okay. So as I said, I sketched the proof. So, and actually, I just maybe list the fact that is needed, and maybe leave the proof really to you. So, the first fact that is useful here to prove this is, the fact that A1 is an interval. Which means that it's said differently, if you want, this is a ring object. In fact, this is of course stronger. So let's say interval means that there exists a multiplication with a unit and a 0, as you can really easily write down. So why this is useful to know that A1 is an interval? This is, in fact, as a consequence of this fact, we have so it followed that a presheaf is A1 invariant if and only if the two maps given by the 0 section and the unit are equal. Right? So if you have a presheaf and you want to show that this presheaf is A1 invariant, it's enough to check this. And this is easy, this is kind of easier to check for this particular object. Okay, because then you need to construct a homotopies between these two things, and it's somehow this is given by the simplicial structure and the multiplication, maybe. Okay, so this is yeah, the first fact which is useful in this proof. And actually, also, I should say that for a consequence of this fact also is that, for example, you can see that the map from K to internal home from some IN K is an A1 equivalence. And again, maybe I say it already. So how would you prove something like this? You take the 0 section, and then it's enough to show that mapping to the 0 section and mapping back to this object is homotopic to the identity. And you do this by using the multiplication of A1. Okay, so and of course you see if from this we already know that this property. Okay, I hope this is clear. All right, so this is because going to K at fibrant, this is an état local equivalence, and then using these A1 equivalences, we can show that mapping to this singular, this is état local equivalence, and this is A1 equivalence, which follow from this. Okay, so this would show that already the first claim. And then the second fact, which enter in the proof, is that so the class of étal fibrant complexes is closed under filtered colimit. Right. This is more concretely. This means that the étal cohomology of some scheme X commutes with filtered colimit. Right, so if you have a complex which is written as a filtered colimit, to compute étal cohomology, you can compute the cohomology of each of the complexes and then pass to the colimit. So this is used, in fact, to show this. To show this property. So in fact, it's easy to see that this complex is already A1 invariant. This is again just a simplicial matter. You have to use this, and then it remains to show that this complex is also étal fibrant. And to do this, you write this complex as a filtered colimit of things, which you obtain by truncating or by applying a truncation of the Suslin-Voivodski construction, where it's easy to check that the thing that you get is étal fibrant, because it involves only a finite. So, I mean, this guy here. So if I put here, So if I look at home with any object with value in something which is fibrant, for example, K étal fibrant. This is étal fibrant, right? Some problem might happen when you take the total complex. This is some kind of colimit procedure, and you need something to some property to be able to show that this guy is étal fibrant, and this is fact 2. And so fact 2 is only true because I work with rational coefficient and because the base is of finite dimension. Okay. Okay. So this is so these are somehow the two ingredients which are important for the proof. Okay, so of course a natural thing would be to try to see if one can do the same thing for the P1 localization. And yeah, it's not difficult to see that we run into problems immediately. So indeed, these two facts somehow are not available anymore. Okay, so we just have seen that the localization A1 et al. Can be given by the singular complex composed with a fibrant replacement functor. And so we would like something similar for the for the P1 CFT localization. So the question is there a similar thing for the functor loc? Let's maybe forget about A1. Just put P1 delta and maybe CFT. Right, so this is the question that I would like to address today. Okay, so as I said, if we try to naively repeat the same story, so we get into two problems. So we have two problems. So first is that P1 delta is not an interval. And second is that the cohomological dimension of this CFT topology is infinite. All right. Okay. Now, so I try somehow to explain a solution to get around these two problems today. But let me maybe first say the following. So the first problem, so maybe problem 1, this is not so serious, in the sense that one can one can find a satisfactory solution to this problem. But somehow problem 2 is really serious. I'd say it's very serious. And we will really have to do something something serious about it in some sense. So yes.
Problem 2 is also true for the topology.
Problem 2 is?
It's a problem.
No, but I said that it's not a problem in the topology because I work with rational coefficient.
So it's Navier. So you like recall the Navier topology.
Yeah, I mean, okay, I know that. Why do you want absolutely to speak about this?
No, I don't want just the thing that also the cohomological.
Yeah, I mean the way that the way how you could use the Nisevich topology, for instance. But it's also known that if you have an Ital sheaf, then its Nisevich cohomology and Ital cohomology is the same Poisson coefficient. Okay, so yeah. So problem 2 is serious, and one has to somehow at least for some time abandon the use of the FC topology. So one has to find a way to do the same thing without mentioning at all the Fourier topology. Okay, so and I'll start now by explaining how to construct a localization functor for something which is not an interval. Okay, so maybe this was some kind of an introduction, maybe to today's lecture, and now I start really the paragraph, which is what is it, 1? Oh, I don't remember. It's 2, 3. Okay. So and what I want really to do is to so here I will work without topology, work without any topology, and so describe a model for the P1 delta localization, or more generally or more abstractly for the E localization for some abstract object E. In some site. We will see this later in a moment. Right, so this will be something which will work really in big generality. Okay, so let me introduce some notation and some definition. Okay, so all right, so it will be somehow, I think, easier to work in the following abstract situation, at least for a while. So I'll be so I take D an additive, maybe a pseudo-abelian category, and I assume that I have F, so an endofunctor, so additive endofunctor of D admitting a right adjoint, denoted by G. And I assume that F is endowed with two natural transformations. So it's called P, and this is from F to the identity endomorphism, and then S from the identity to F, and such that P composed with S is the identity of the identity functor. Okay, and so in this case, I'll denote by P prime identity to G and S prime G to identity, then natural transformation that you get by adjunction, so deduced or obtained by adjunction. Adjunction. Okay, and then I also denote by phi. Let's be the composition of F with G. So phi comes with 3 natural transformations. So that is phi to identity, which I denote by delta. So this will be the co-unit of the adjunction. Co-unit of adjunction. Then there will be sigma phi to identity, which is, so this will be equal. So that's somehow one way to go from phi to identity. You apply P and then you apply S prime. So P composed with S prime. And then there is, I think, how did I use this? I think rho from identity phi. And this is probably P prime times composed with S. Okay, so we work in this situation. So maybe I give you the example that one should keep in mind. Maybe you have already guessed what is the example. So, of course, the example that I'm interested in is you take D to be the category of complexes, sheaves on some side, but let's be concrete, and so I'm working on this side, maybe with coefficient Q vector spaces. This will be my D. Then F will be P1 delta tensors, and so the right adjoint G will be Trendelenholm P1 delta, and so of course P will be induced by the only map from P1 delta to spec K, and S. So I could take, for example, the infinity section at infinity. Or I could take 0. It doesn't matter. Okay, so this is the example that I have in mind. Okay, so let's see. So we have the following lemma, which is maybe also good to try to translate it in this situation. So the lemma says the following. So I work in this situation, and so the lemma says that for an object in D, the following conditions are equivalent. So saying that the map P prime going from X to Gx is an iso. It's the same as saying that S prime from Gx to S to X is an iso. And this is also equivalent to say that the two maps sigma and delta from phi x to x are equal. Okay, and so in this case, so if this is the case, we say that x is F invariant. Okay, so you see, so this notion in this particular example is the same as saying that x is P1 delta invariant. Okay? So before explaining the proof of this lemma, which is actually quite straightforward, just want to say that this is the analog of so what we have for so as I said, if we know that if we have an interval, then we can rephrase the property of an object being local for this interval or invariant for this interval by saying that two maps are equal. Okay? So this is somehow an analog of this in the situation where we don't have an interval. So let me prove this lemma. All right, so let's see. So clearly, A and B are equivalent. So this is really clear. So what I will do, I will prove that that A plus B is equivalent to C. And so I start with this direction. So I assume that A and B are true, and I want to show that C is true. So by A and B, we know that, so by A plus B, we know that the endomorphism of Gx, which is given by P prime composed as S prime, is the identity. This is the reformulation of A and B. Okay, so going first to X and then from X to Gx is the identity of Gx. So so I use this, and so we consider so therefore it is enough to show that the following composition, that the two compositions are equal, where so we go from Gx to Gx by this P prime equals S prime, and then here we have these. Sorry, I have to put an F. And then here we use the following, so the two map. Okay, so if I can show that the two compositions are the same, I'm done. Okay, and so we check this. So let's see how can we do this. So see, we have the map to fx. So like this, and in fact, it's actually enough to do these two compositions. All right, so let's see. I'll try to do this here. So I compute maybe the first one here. Okay, so I want to go. So I want to compute fx going to fgx, and this is going by p prime. And then I want to apply the unit. So the unit. Okay, so this is really by definition of the way you get p prime from p. This is p. Okay, this is how p prime and p are related by the adjunction. It's via this. So this is p. And so now I try to do the other one. Let's see. Maybe I should not. I should keep this. I don't know. Okay, let's see if this is needed. Okay, now I look at fx. Fgx. Again, this is p prime. And then I can go to x. This will be by s prime. And then to x. And this will be by p. Okay, and this is my sigma. Yeah, now we see again this is this is fine because this is identity. Okay, right. So the two maps are given by p. Does this prove what I want? Yeah. Okay. Okay. So my goal was to show that these two maps are the same, and I've done this. Okay. So now we assume that, so now we do this direction, so we assume that C is satisfied. And I want to show that A and B is also satisfied. And so again, it's enough to show as before, so enough. So it's enough to show that P prime composed S prime as an endomorphism of Gx is identity. So this is what I will check. Okay, so and to do this, so we claim this map P prime S prime. This is given by the composition following diagram. So maybe take it from some place. Okay, so claim that this is given by you go from Gx, you apply eta, so this is the unit of the adjunction, to get to Gf Gx. Right, so you apply the unit here, and then you take G sigma to go to Gx. Okay, so why this is really this map here. So you can see it as follow. So you have the following commutative diagram. And this is supposed to be P. Yeah. This is commutative. Again, why? So remember, this is essentially S prime composed. So this is S prime composed with P. So this is clearly commutative, and this is commutative also clearly. And now, if once you have this, you see that that this map is yeah. So this yeah. So this is P prime, I think, and this is what you want. Okay. Okay. P prime is related to P by this this community. Okay. Yeah. So now that we have this, then we are done, because then this is also G, the co-unit of the adjunction, and it's well known that this is identity. Okay. That's it. So it's just to show that it's really straightforward verification. It's probably better that you do it yourself than listening to me doing this on the Blackboard. So I'll use this to construct. So this principle to construct a variant of the Suslin-Voyvodsky construction. All right. So here's how it goes. So construction. So yeah, we define a cubical endofunctor that I denote by SF of T as follow. So for an integer n, I denote by, so I set SFN. By definition, this is phi composed with itself and time. Yeah, by the way, I should have asked, do you want me to remind you what is a cubical object? Huh?
Yes.
Okay, so I'll do this. All right, so I try to put it here. So you know what is a simplicial object, right? So a cubical object is the same as a simplicial object, except that you use a different category. So so we think this is the usual notation. We denote by cube. This is so the category of cubes instead of simplices of cubes. So precisely, this is given for so the nth cube. Okay, the nth cube is just you take the simplex one. I don't know how should I, maybe the usual notation is like this. Okay, so I usually denote simplices by a number underlined, maybe a bold number, and so this is here is this category. So this is the first, this is the first cube, and then the nth cube is just this to the n. Okay, so it's you can think about it as an ordered set or a category, and then the category of cubes is spanned. So this is spanned by the projection from delta 1 to delta 0. Right, so this is delta n. Right, so this is a unique map from delta 0 to delta 1. So this is just a point. Here you have 0 and 1. You project, and then there are the two sections given by 0 and by 1. Right, so it's the category spanned by this in some sense. So and you will see it maybe on the examples better how this works. Okay. Yes.
Did you say one cube? Set of
one cube, nth cube.
the one cube. What is the one cube?
So one cube is just this. Is a segment, is a line, if you want. It has it's an ordered set with two elements, 0 and 1, and a map from 0 and 1, and it's also the simplex 1 in the category of simplices. Okay. Right. So there are maps. Maybe I should write it like this. So there are maps like this: delta n to delta n minus 1, and these are indices. So pi, and this is I think for 1 I n. So this is just projecting on the ith factor, forgetting the ith coordinate, and there are maps the I epsilon from n cube n plus 1, and this is inserting. So epsilon will be either 0 or 1, and it corresponds to inserting 0 and 1 in the ith place. Okay. So this is for 0, for 1, I n plus 1. And then so a cubical object is just a functor, a contravariant functor from the category of cubes to any category. Okay, as we do. So here I'm speaking about a cubical endofunctor. So it's a functor from the category of cubes to the category of endofunctors of T. Okay. All right. So it's the n's. So the degree n is given by composing n times phi. And then I need to tell you what are the morphism. So pi star from Sn minus 1 f to Sn f for the I less ei less n. Okay, so this is given as follows: is the composition of I mean, okay, so this is phi. So you write this as follow. Just let me check. N minus c. Okay, and then you apply the natural transformation rho here, so which goes from identity to phi. So then you would go to phi phi minus 1, phi n minus I, which is phi n. Okay, so this is the map corresponding to the projections. Okay, and then so these are called the degeneracies, I think. And so the phase map are so di epsilon star going from S f n plus 1. So these are given as follows. So you have phi composed n times. You decompose this, sorry, n plus 1. So you decompose this as follow. N plus 1 psi. And then you apply here so the two possible maps, namely sigma and delta. So here this will be for epsilon equals 0. This is for epsilon equal 1. And then you go to phi compose minus 1, compose identity, composed phi n plus 1 minus I, which is phi. Okay, and then it's fact that this is defining a cubical object, so you have to check that some compatibilities between this and everything somehow follow from the fact that, so here we will use that rho composed with sigma. Sigma composed. Okay, well, one of them I don't. That is identity. It's the converse. I think. This follow from this proper identity. Now, there's another construction on cubical thing, that cubical object that I need to remind you about. So again, reminder. So if you have Q, a cubical object with value, so in an additive pseudo-abelian category, so we can associate to Q a complex as we do for simplicial objects. Okay? So so here there is the first naive complex, which is not the right one, but I introduced this because I need it. So it's denoted by C dot sharp Q. This is defined as follow. So in degree n, it's just Qn, and so and the maps. So the differential is given as follow by just taking the alternating sum with some sign of ti1 minus ti0. So you can cook a complex like this. it's not the right one because it has some junk in it, and so to get the right one, we one showed that in fact decomposes. So maybe assuming that your category is pseudo-abelian, you get there is a decomposition like this plus some extra complex, and this is the C is the right one, and one can define it. So I can tell you what is the C. There are two ways to write it down. So you can take C and K to be the intersection of all the kernels of DI0. Right, so you look at one of the faces. So one. So the DI0, you take the kernel, you intersect them, or it's also the same as the co-kernel, or maybe like this. You take Qn and you mod out by the images or the sum of the images of the Pi upper star, the degeneracies. Okay, so there are two ways. It can be shown that they give the same complex, and that it's split as a direct sum and offset. Okay. Any question about this?
So you say that given a cubical object, you construct another object with C star.
So for a cubical object, you get a complex. Yes. This is a complex in D. So just as the usual sense, a complex. Right, so this is the analog of the usual construction that whenever you have a simplicial object, or like for example a simplicial group, you can get from this a complex, right? And this is the analogous construction. Okay. Okay, so with this we have the following easy proposition. So let's take an object A in D. Okay, then the two maps induced by sigma and delta that goes from phi applied to the I think this is called the simple complex. Maybe I set it to Q. So the simple complex is set it to S F A. Okay, they are homotopic. Okay, so this is pretty straightforward. Maybe I should say also here that the same is also true. Same is also true for the other variant. Okay. So maybe here very quickly. So why this is the case? So the point is that this complex. So it's enough to do it for the dash one. Okay, because the first one is a direct summand of the second one. Okay? So enough to do it for C sharp, and so it's clearly easy to see that, it's easy to convince yourself that this thing here is the same as that. Okay, so the associated, so if you apply phi to this complex C dash of something, it's the same as the associated complex to the cubical object that you obtain by shifting the degrees. Okay, I mean it's clear, pretty clear. You just add a copy of phi everywhere, right? So it's really clear. And moreover, the two maps that we are interested in are just given by the faces, like they correspond to D10 upper star and D11 upper star. Right, so you get. Okay, and now it's a really general fact that whenever you have a cubical object, and you do this construction, you shift the degrees and look at the two maps that you get from the faces, that these two maps are homotopic. And the homotopy is actually given by the identities. If you write down the complexes, you see that you have identities, and that's it. Okay, so from this we get this nice corollary. So we assume that D is abelian, so it's an abelian category, that F and G are exact functor. Maybe it's abelian plus infinite sum if needed. Then given a complex K in D, the homology of the complex that I wrote like this, dot cube S K, which is by definition this is a total complex associated to C, associated to SFQ. Okay, so whenever I have a cubical complex, I denote by dot cube the total complex that you get by the natural construction. So the homology of this is F invariant. So Okay, I mean this is really clear. Again, from the proposition, what do we get? We get that if you pass to homology on this thing, so CSFA, that the two maps are the same. Okay, so this is just we have two homotopic maps, they induce the same map on homology. These are equal. And now we use the fact that phi is exact, so we can permute them. Okay, and then from this we use this, the first lemma today to get what we want. Okay, so another, so somehow maybe before going on, so let me maybe say where we are going. So to this point, I somehow essentially showed that if you want, so we have this. Okay, so this dot cube SF transform a complex into a fibrant one. Fibrant here with respect to yeah. So maybe just in quotation. I don't want to. Okay, but so this is not enough to get that this is a localization functor. We still need to know that the map identity to this is given by weak equivalences. Okay, and so now we try to see it, to what extent this is true. Also. Okay, so to do this, we use the following again simple proposition, which is the analog of the one here. Actually, I could maybe there's no need to write it down because it's still here. So let's see. So I think what I want is this. Okay, all right. So this is still true, and the proof is the same somehow. And here you have to put I don't know the last one. So this is true. And okay. So why do? And so this we use to prove the following corollary. Okay. So again, we take A, an object of E, and so that now the claim is that the two morphisms going so the map induced by P, which goes from C of SF applied to FA to C SF applied to A. And the other one, maybe I write it here. Okay, let me write it like this. So we have P and we have S in the other direction. So these two morphisms are inverse of each other up to homotopy. So again, this is not so surprising. I mean, if you think in terms of so if you are dealing with the A1 case, I mean, like, trying to construct the A1 localization, what you are doing here is that just you are taking A1 tensor something, and apply to it the localization functor, and you are saying that this is going to be the same thing without tensoring with A1, okay, which is kind of expected. So it's not a surprising statement. So the proof is, again, just playing with adjunction. So, of course, we only need to show that the composition SP is homotopy to identity. Okay? And so we claim that this composition is given as follow by first you go from FA, sorry. Maybe let's see. It's obtained by applying this construction to the following composition. FA, the unit to go to FGF. Okay. So here you apply the unit here, and then you go by sigma to FA. Okay, so I leave this to you. It's really just a simple game with adjunction. Right, I mean, this is composing S prime and P, so eta and S prime give you back S, and so on. It's very easy. Okay, so this is our map, and we want to show that this is identity. But now you see by the previous proposition, we know that. So this is phi. Okay, we know that that sigma could be replaced by delta without changing the composition up to homotopy. This is what the previous proposition tells us. Okay, but once we have this, we are done, because then going like this is identity, and so we are done. Okay. All right. So now we come to something slightly more interesting, which is the following proposition. I mean, it's interesting in the sense that it's slightly more complicated to prove, but it's still quite easy. So we take an object in D, which we assume to be F invariant. Okay, then the obvious map from X to C dot SFX is homotopic, or is an isomorphism up to homotopy. Is an iso up to homotopy. Okay. Again, I mean, it's not a surprising statement. If you think in terms of A1 invariance, it's kind of clear. maybe the only surprising thing here is that I was not able to find a direct proof of this. So the proof is a bit, you see, tricky. So I don't know. I would expect to see something straightforward here, but all right, so here's how it goes. Okay, so what the assumption is that the map x prime gx is an isomorphism. This is our assumption. Okay, so we can go. So for general x, I could I have a map from SF n minus 1 fx going via p prime to SF n x. Okay, is this clear? So I'm just adding. So right. So if I apply p prime, I would be adding just a copy of phi, and this is just SF n x. So this is true for then one, and so we have isomorphism like that. And furthermore, so this map somehow equalizes the two differentials which one? I think it should be the last one. Yeah. D star in 0, D star in okay, so why this is the case? I think you should just show that. Yeah, I will not maybe do it. Should I do it? Or, yeah. Maybe I do the first case just to see what's going on. So I'm claiming that fx going to f gx going to x by either eta or by either delta or by sigma is the same, and it's actually true because I think both of them are equal to p. Okay. All right. So we have these two things are equal, and since this is an isomorphism, they are equal without any they are already equal. Okay. So these two maps are equal in this complex. Okay. So in particular, they do not contribute when I look at the complex C dash. Okay. So, and as a conclusion, we see the following: we see that the complex C dash SFX, sorry, SFX decomposes, has a decomposition into two parts. So as follows. So we see a copy of x put in degree 0, and then plus C dash SFX shifted by 1. Okay, and so the map is given by the map is going like this, and it's induced by this p prime. Okay, so in degree 0, you see we have x0, and the first differential is indeed 0 because there are And so this splits a direct summand, and the rest of the complex you can identify with that one there. Okay. Good. Now you see, on the other hand, we have a map. Okay, x0 plus c cross c sf x shifted by 1, and this is given by the map S induced by, so it's identity plus the map, the natural transformation S. Okay, and by the previous corollary, so this is actually an iso up to homotopy by previous corollary. Okay, right, so this complex turns out to be quasi-isomorphic, or isomorphic up to homotopy to that one. Okay, now you see I have this surjection to C dot SFX. Right, so this is a direct summand of this, and it's very easy to see that if you compose all these maps, then this here goes to 0. This goes to 0. And why it goes to 0? Because you see this is obtained by modding out by the degeneracies, which are the images of rho, and the image of rho is somehow this guy is this is the image of this is contained in the image of rho because of this S here, I think. I mean, there is S and there is P prime, I think, somewhere here. And S with P prime is really rho. So this is really going to 0 when you mod out by the image of rho. Okay? Right, so what do we get when we do this? But then, so yeah, since this goes to 0, the conclusion is that the natural map from x0 to this complex fx is surjective up to homotopy. So in the sense that it has a section. Okay, so if you think about it, you have a direct sum mapping to something which is a surjection, and one of the factors goes to 0 by this map. Okay, so the other one is actually also surjective to the first. Okay, right? But then you see this is actually it's also a direct summand. Also a direct summand. Why? Because I mean x0 is a direct summand of this bigger thing, and it's contained. I mean, there's also there's also the map in the other direction which contains x0. Okay, so x0 is a summand of this, and the inclusion map is surjective up to homotopy, so it's an isomorphism. Okay. And I would be happy if someone can provide a better proof of this. So yeah, this is all what I have to say in this very, very general situation. Now I go to a slightly more specialized one. So from now on, we'll take C, a small category that, for example, you can think about it as being the category of smooth varieties or smooth foliation, admitting a final object, which I denote by star. We take D to be the category of complexes of P sheaves on C, maybe with some coefficient and some ring lambda. And then we fix an object of C, which is curable. I don't know if this is standard terminologies. And I mean by this simply that direct product with E exists. Okay, you can speak about E times X. We assume that we have that E is pointed, so E is pointed. That is, we have a map from the final object to E, which I call S, and we denote by P the map to star. And again, then F, the functor F will be tensoring with E, and the functor G would be coming from E. Okay, so I now specialize to the situation. Okay, so and maybe I should write it here. So let's see. A complex, so a complex in D, this complex on C, is E invariant if the homology is F invariant. Okay, so just okay. So then we have the following theorem. Saying that, so let L be a complex of pre-sheaves on T. Then, so I define, okay, I should maybe define this before. Notation. So we set SG with E. So it's like a singular complex for E of L. This is by definition the total complex associated to the cubical complex obtained by applying SF to L. Okay, this is the notation. Okay, so then the theorem is that, so under this hypothesis, SG E L is E invariant, and the natural map from L to this is an E local and equivalence. Okay, so said differently, this functor is giving us an E localization functor on D. All right, so let me prove this. We are almost done. I mean, we just need to use what we've done before in this situation. So we already know that this complex is E invariant. This is by previous corollary with maybe slightly different notation. Okay, so this is as we know. So what we really need to check is that the map. So we need to know that in order to prove that the map is an E local equivalence. So this is a question that we need to answer. Okay, so to do this, we argue as follows. So we start by fixing a map from L to K, which is an E, which is sometimes we fix an E fibrant replacement of L. Okay, so this will be E local equivalence, and this is E fibrant. And E fibrant is simply E local, E invariant, the same notion. Okay, so I take a map from L to something which is E local, E invariant, and the map is an E local equivalence. This exists. I know that such a thing exists, and I apply to its functoriality to get SG EK. So we have the following square, and so what I will show that I show that these two things are quasi that this is a quasi isomorphism, and that this is a quasi isomorphism. And so if I can do this, then I'm done. All right. And so this is what I want to show. Okay. So how does it work? So let's start with the Okay. This is the easiest one. So the fact that K to S. So to prove that this is a quasi isomorphism. So we use a spectral sequence to show that when you apply this on homology, it's okay. It's a quasi isomorphism. And this is okay by the previous proposition. Yeah, we know that this map is actually an isomorphism up to homotopy. Okay, so this is fine. Now let's deal with that one. Okay, so for maybe I give a name to this. Let's see. For SGE L to SG. Okay, we use the fact that the map L to K is a retroact of a transfinite composition of maps with co-kernel of the form E tensor some complex of presheaves. And so this is a general fact about localization. So essentially this is the only thing that you know about, which is not completely trivial about Boothfield localization, is that when you make something fibrant, then the map from the initial object can be written as a composition of map where the cone here or would be of this form. Of this form modulo something. Okay, so should I say more about this? Is it so surprising, or should I continue? Okay, I mean, actually, I can finish the proof. Sorry. Okay, no. So if we know this, then we are done, because then we are reduced to show. So here I use the fact that this functor commutes with filtered colimit, with composition, with cones, and so on. So we are reduced to show that SGE of something like E tensor something over something is contractible. And this is again something that I've seen before. So the map, so the map induced by P, for example, or by S, give me weak equivalences, or give me quasi-isomorphism. Okay, this is the corollary saying that CSFFX to CSFX is an isomorphism up to homotopy. Okay. You are so surprised. What's happening? Huh? So this is just another notation for that, right? Okay. Is this clear? All right. So we have our localization functor now. I need to give you one compliment about this. So later we will be actually we will have to localize with respect to a family of objects. So we need to explain how this extension, how one can extend this to a family of objects instead of one object. Okay, so let me just introduce a new situation. So C and D as before. And now instead of taking one object, I will take a family of objects. So now just by E underlined, this will be a collection of objects indexed by some set V. And they are as before, so there will be queryable, pointed objects. We will have a map SV from star to EV, and then PV to the point. And of course, SV will denote tensoring with EV, and GV will be homing from EV. Okay. And the notion of E underline invariant object is clear. Okay, so it's just should be true for every object of E. Okay, so and again, the goal here is to construct an explicit localization functor, so something like this. Okay, explicit E localization functor. All right. So unfortunately, I don't have a very nice answer to this question. So the answer is a bit annoying in some sense, but it's good enough for later. So I explained this to you now. So to do this, I need to fix a choice, and so this is a choice of repetitive order on V. So I need first to define what is a repetitive order on V. So repetitive. On the set V or any set as a surjective. So as a surjective map. So I call it L from a set that I denote by V vectorial to V, okay, which is surjective. So surjective map. Okay, where V is a totally ordered set, and such that the following condition is satisfied, namely that for every finite subset V, and any element of V that exists V prime in V vectorial larger than every element of A, and such that L V prime is V. Okay, so and it's kind of easy to see that such a thing exists always. All right. Which one? The V under the V. So that this is the V vectorial is a choice. Just we don't. But for V, yeah. Okay. It will come today, but not now. So yeah. So I will apply this in the situation where. So you see, before I was always dealing with P1 delta. This was the object that I'm just interested in. But because I will have to, I will not be able to use foliated topology. I will be forced to consider some family of P1 delta which are not trivial. Especially the thing that we have seen last time. This, see, we had this particular foliation, which was whose underlying total space was P1 times A1, and it had a map which was diff étale to A1, and so we will have to consider object of this form and variant of this. This will be the family of E. Okay. So this will become, I hope, clearer later today. Okay, so here's a construction in the situation that I considered before, and once we fix such an order. Okay, so make the following construction. So, yeah. All right. So just for V in V vectorial, I'll denote by EV instead of ELV, and similarly for SV and so on. Okay, that's the notation. All right. So, okay, we do the following. So given a subset of V vectorial, finite subset, finite. We can, since this is a totally ordered set, we can order A accordingly. So we can write A as A1 strictly smaller. And then so I can define SG singular complex for the family E, but restricted to A. So this is a functor, and I define this just by composing the functor that is associated to like this, using this order, of course. This is important. Okay, is this clear? Okay, so I use the functor that I defined before. I compose n of them following this order, and I look at this functor. Now, whenever I have an inclusion that is an induced functor like this, which is given just using the unit, the natural transformation from identity to SG E of something. We can construct such a natural transformation, and then we define SGE, the thing that we are looking for. By definition, this will be the colimit over all subsets, finite subset of the vectorial of SGE. Okay. It's not, I mean, the actual construction is not so important, but just to know that it exists. And then with this, we have what we want. Theorem. So L a complex in D. Then SGEL is, let me write it like this, is an E fibrant replacement of L. Okay, and the proof is just using the previous theorem and the construction. So I leave it to you. So I want to end this section with the following remark and maybe a statement, a corollary about so what happens if there's a topology, or what goes wrong when we have a topology. arc. So assume that we have a topology on our category C, and that we are really interested at the end. So we want to understand the E tau localization. Get a model for the E underlying tau localization. So of course the naive I guess would be to say, okay, we just look at, we have the thing which work without a topology, so let's use it. Yeah, by the way, there are underline, there's an underline there which is missing. Okay, so let's use it and compose it with a tau fibrant replacement. Okay, so the guess would be this provides, this provides an E tau lock functor. So I've told you already a reason why not to expect this in general. So if tau have infinite dimension, infinite cohomological dimension, we cannot expect this. So let's see, maybe wrong for two reasons. Wrong for two reasons. So first, the one I have mentioned before, namely that in general, so if tau is not has infinite cohomological dimension, then it cannot be expected. That this functor preserves tau fibrant object. So if you compose this, then the result will not be in general tau fibrant. So there's no chance that this will be a fibrant replacement. But there's actually an even worse. So even if tau has finite cohomological dimension, this cannot be also true. So actually, even if tau has finite cohomological dimension, there is a problem with such a definition. I don't know. Should I maybe ask if somebody know what is the problem or have seen the problem? Okay, so the problem is the following. So you see, in the A1 localization case, we had the complex which was built out of these kind of functors. Okay, and these kind of functors, these are right adjoints. They preserve fibrant objects. Okay, but in our case, so we are dealing with something a bit more complicated. Namely, we are looking at these functor phi v, which are defined like this. So they are tensor product with, so it's a composition of a left adjoint with a right adjoint. Okay, so this guy in general do not preserve or do not respect fibrant objects. So there is, so this failure of preserving fibrant objects is actually present already at the finite stage. So we don't need to pass through the colimit to get this problem. It's already in the building blocks of this functor. But there is one case. I mean, okay, there is a stupid fix to this. Stupid fix, which is the following corollary. So assume that cohomological dimension is finite and tensoring with E preserve fibrant object. Then in this case, then SGE to fibrant is a good model. It's a model for E tau localization. So I should say, I mean, this thing here, for instance, is this property is wrong for P1 delta. Why it's wrong for P1 delta? Because yeah, you should think about it yourself, I think. So yeah, it's not a good notion. I mean, this is in practice never happening. But in fact, we will somehow impose something like this. We will. So I tried to explain this today, not very precisely, but we will somehow work in a situation where this will be indeed the case. That the tensoring with our object that for which we want to localize will preserve fibrant objects. Okay, so it will be a slightly artificial situation, but where things can be where things somehow works well. Okay, so I propose that to take a break now and maybe start in 10 minutes. All right, so maybe I just want to say a few words more about the fact that if you tensor with an object, then you somehow destroy the property. So destroy the low fibrancy property in general. So I will maybe do this in a situation which is that you are familiar with. For example, let's work on smooth varieties, and for the Étale topology, and see. And let's take E to be, for instance, P1, or any variety. It doesn't really matter. So just to understand what why tensoring with E somehow tends to make things not non-fibrant anymore. So being étale fibrant somehow is closely related to being an étale sheaf. Right? I mean, this is really something like a homotopical version of being an étale sheaf, right? And so maybe let's look at what happened if I take a sheaf and I tensor this with P1, okay? And see if you have if you fix X, and let's say you have F an étale sheaf with varieties, then the section of P1 tensor F at X, so these are equal to, just you take morphism from X to P1 as a set, and you tensor this with a section of F at X. Okay, so somehow it's yeah. The thing is that there are more and more sections when you replace X by an open subset of X. Okay? So somehow for example, if X is proper, then there will be very few maps from X to P1. But then, if you go to the generic point, there will be a lot of points. Okay, so and yeah, it's actually not really difficult to really see that this is not this cannot be really a sheaf. It's already not a sheaf. And in fact, that there is only one, in some sense, there is only one situation, essentially, where tensoring with E preserves a fibrant object, étale fibrant, let's say. For E, a pre-sheaf, let's say on smooth varieties. And this is the case where E is actually constant. So if E is constant, if E is, I don't know, so you take a vector space or anything, and you take the constant pre-sheaf, then this will preserve fibrant objects, because when you tensor with V, you are just taking a direct sum of copies of your sheaf. You can do a slightly different. There's a slightly different sheaf which also does the same. So this is the thing I denote by AT empty set. This is so there is a topology T empty set, which is a topology where you just, which is essentially the coarse topology, except that you can cover your empty scheme by the empty family. So this is a very stupid topology. It means that you replace your pre-sheaf by, it's the same pre-sheaf, but you put 0 at the empty scheme instead of the values of it. Okay, so this guy also preserve tensoring with this also preserve fibrant. In fact, there is I think there is no other examples of pre-sheaf with justice. There are these two things. I mean, even if you take the constant sheaf, then tensoring with it will not preserve fibrant. And so yeah, so this is just somehow to maybe to prepare to somehow, I think if you keep this in mind, you might understand better what I want to say later. Okay, okay. So now what I want to do is let's go back to the thing that you are interested in, namely to the P1 delta localization, and see what we can do. Okay, so what is this paragraph? Okay, so back to the okay, let me again remind you what we are and what we want to do. So we essentially have from last lecture we essentially have constructed some kind of a level-wise weak equivalence between the spectrum that you are interested in, namely the spectrum that represent the ramp cohomology on foliation, and something which is a localization like this of an infinite suspension spectrum on the ramp complex. All right, so this is somehow what we want, and we want somehow to be able to use this, and to be able to use this, we need to understand somehow concretely what this functor is doing. And I told you that this is not possible, essentially because of this, of the topology here. And so there are two, essentially two problems, as I said. Maybe let me list them again. So two issues with this formula. That first, CFT is a terrible topology. It has infinite dimensional, infinite cohomological dimension. One thing, and the second thing is that as I said, tensoring with P1 delta destroys fibrin, so fibrin C. So these are some of the two main issues that somehow provide us from being able to use this kind of this formula. So and there's nothing to do. I mean, this is how it is. And in fact, the only thing that I could come up with is to revisit somehow the whole proof, let's say, of this isomorphism, and see if one can somehow save some to get a better, maybe a better formulation or a better state, to get something that you can explode. So I will not do this to you. I will just maybe try to say a few words. I mean, so what that you could also maybe you see if you look also at the proof, and yeah, okay. So it will be a little bit vague, but. Okay, so we can. So if you look, as I said, if you look at the proof, you can observe the following facts. So some observation. On the proof of star. And actually, there will be essentially two observations. But okay, so the first one. So why do we really need to use this psi-foliated topology? So in fact, there is only one place where this topology really is used, and this is as follows. So the psi-foliated topology is used at one place. in an essential way at one place, and this is for the following implication. So say that if K is P1 delta CFT fibrant, then the natural map from K A1 to K X bar E is a quasi-isomorphism. If you remember this, how this was proved, so we would say that, that there is a foliated cover of A1 which trivializes this this guy here. So it means that this guy becomes just a Cartesian product of P1 delta with something, and then we can use the fact that we are P1 delta local to conclude. Okay, so this is where somehow in fact this is the only place really where the Fourier topology is used in an essential way in the proof. This is one observation, and the second observation is the following. So again, if you look at the proof, in the proof we don't use many maps between products of P1 delta. All right. So if you look again at the map, we are not using much about. We only need to know that there are sections from like this. So 0 and infinity, and maybe projections like P1 delta times n to P1 delta n minus 1. So we need to know maybe that P1 delta is scorable, and we need to have these two maps, and maybe we need to have diagonals and so on. So we don't really. I mean, we never use like I don't know. Ramified degree 3 cover of P1 delta. I mean, everything is very simple. So, and so somehow we see we don't. I mean, this is somehow an important point, because you see if P1 delta don't have many maps between them, then in fact what I was saying before will hold true in some sense. Tensioning with P1 delta will preserve fibrancy. Okay, so this is somehow an important point. If we could arrange things so that P1 delta have very few maps between product of so then we can hope maybe to still use this model that I introduced. And also we could also hope somehow to remove the use of the Fourier topology if we could also maybe find a way to impose these that these maps are isomorphism without having to use P1. Okay, so there are two things that we can try to do. First is somehow try to kind of rigidify P1 delta, so somehow remove all the map that we don't need between the product of P1 deltas. And the second thing would be to use as much as we can, for example, the étale topology. And then maybe impose by hand that these kind of maps are isomorphism, instead of deducing this from the fact of from the P1 delta invariance. Okay, so this is the if you want the idea, somehow to try to solve these two problems. Okay, so I will not reprove the theorem I proved last week in this new context. But what I will do, because I mean I unfortunately this is the thing that I need for later. I will have to somehow introduce this context. I mean this new situation where where we can achieve somehow the solution of these two problems. Okay, so I will have to introduce some maybe new category of spaces in some sense, where I can speak about. So I will be speaking about E-bar localization, which would be this variant I mentioned, and then at the end maybe state the analogous theorem that I can use later. Okay, so this is what I will do. It will be a bit boring, I suppose, because there will be a lot of notations and it's maybe a bit hard to follow. But I think okay. I mean, this is what I have to work with later. So I don't know how to escape this. So I have to pass by this. Okay, so I hope you will be patient. Okay, so maybe you can start. I will just state, introduce main notation and then state a theorem, and then this will be the end of the lecture. Okay. And somehow the proof of the theorem that I will state is really exactly the one I gave you last time. It's just in a situation which is a bit more complicated to work with. Yeah, I should also say that if you want really to, for example, to follow the proof of this variant of this, it is done in the paper in this language I will now introduce. Okay, so the paper, I don't speak about P1 delta localization. It is in the last version. It's done in this kind of artificial somehow context that I will introduce now. Okay, so all right, so I start by introducing some notations. So I'll denote by theta over line. This will be the free. So the free category with finite direct product so free category with finite direct product generated by one object, which I denote by E over line, E bar. And so this object admits, so admitting two maps from the final object, so 2 points if you want, so a 0 and S infinity. And of course, we secretly think about this as P1. Okay. So what does it mean to be fairly general? It does mean that whenever I have a finite set, I could speak about E bar over power this finite set, product of copies of E bar. So the objects of theta bar will be denoted by alpha, beta, gamma, etc. And set. So there is essentially unique. There is a unique product preserving functor, which I denote by E over line, that goes from theta bar to schemes and sends E bar to E1 bar, which is my notation for P1. Okay, and so I will be, so the image of alpha will be written E bar alpha on the one. Okay, so these are some just convenient notation. Right, so and the points will be given by the 0 and infinity section of E bar. Okay, so this is somehow what I was trying to say. Is, we would like to somehow rigidify somehow the P1 delta, and this is a way to do this in some sense, right? So this is, you see, I somehow removed all maps between, except the obvious one, between the product of P1s. Okay, so just keep the diagonals, projection, and 0 and infinity section that I need. Okay. Cool. Yeah, maybe. I don't know. Yeah, certainly. But I mean, okay. You mean thinking about n as a set, or?
No, yes, I mean, alpha is just direct products of P1.
Right. Yeah, yeah.
Okay.
I mean, it's like. Huh?
Direct products of P1 and not Pn.
Yeah. Okay. I don't know. I mean, yeah. It's certainly, I don't want to think about alpha as being as being a finite set. I mean, I might want to think about alpha as a finite set, but not as the integer n. It's just, I think this is yeah. No, but it's going to get even weirder. So I'm sorry about this, but all right. So the next weird thing to do is the following. So continue with notations. So now I fix. Let V be a set, an arbitrary set. So I denote by theta bar V. So this is, if you want, this is the restricted product of copies of theta bar. Okay, so i.e. objects of theta bar V are families alpha V, V. So families in theta such that alpha V is a final object except for finitely many V's. So we still have a functor from, we still have, so maybe first let's see, so if you have a map, then this gives rise to a functor. Okay, so I maybe not write it down, but you see what it does. It sends a family. So if you have a family indexed by v, you get a family indexed by u by so you take if you have an element of u, you look at the fiber of by this map and you take the product. Okay, is this clear? Should I write it down? This is f. Alpha will be sent to the family product v in f minus 1 u alpha v indexed by u. Okay, this makes sense because of this condition. And we also have, so in particular, we have a map from theta v to theta bar, so you can compose bar, so we get, again, we get a map like this, a functor like this. Okay? I still call this e bar. Okay, so why do I do this weird thing? So maybe I can explain quite easily. So okay, so why looking at this? So here's a remark. So in practice, and this will be the case later, so V will be, so V will be a set of closed differential form on a scheme, on a smooth scheme. On a smooth or maybe, or more generally, V will be endowed with, so this will be a set endowed with a map, small omega from V to Z1 Durham of S. And so if we are if you are in this situation, then we can somehow, if you want, enrich the functor there with some natural foliation structure. So more precisely, so in this case, we have a functor. We have a natural so here. So I'll denote this by E bar index S and the foliation omega. Okay, so this would goes as before. So but now it goes from theta bar E to smooth foliation over S. So how does it work? So so it can be characterized as follows. So it's the unique. It is the unique one respecting product, and on generators it does the following. So and sends E bar v. So what is E bar v? Maybe I should. So E bar v, this is the family sending v to E bar and u to star for u different from v. Okay, I call this E bar v. So it sends E bar v to the foliation E bar s over E omega v. So it's a foliation which depends on a differential form, closed differential form, and I can write it down. So I would write down maybe just the open set E. So this is it's a compactification of E the same way as x bar is a compactification of x from last lecture. Okay, so this is just S with a variable, and its inverse, and the variable you should think about it as E exponential of the primitive of omega v. Okay, and then you can write this down in a formal way. So you mean as a scheme is just S cross E1. And you impose the differential equation, which is d of the omega is omega, sorry, is E omega times omega. Okay, it makes sense. So since omega is closed, you can check that this is a foliation. Okay. So one should think about this V as a way somehow to parameterize some kind of some foliation structure on this functor, if you want, or this diagram. Okay. All right. So let's continue. Okay, and I also need to use the language of diagrams of schemes at foliation. So I just remind you about this in case you don't know this. Okay, let me remind you about the language of diagrams. So maybe I do it in a I do it for schemes, and maybe yeah, and you can imagine what it means for other kind of spaces. So a diagram of schemes is simply, so it's just a functor S from E to schemes, okay, where E is a small category. And this is usually denoted So usually denoted by just S comma I. Okay, so just a collection of schemes with arrows between them. There's a notion of a morphism of diagrams of scheme. Maybe I should say it at least once. So if you have TG and SI, so you can speak about a morphism between these. So what would be a morphism? So this is the data of a functor. Let's call it theta, and a natural transformation from T to S composed with theta. Okay, and if you have a diagram of scheme, you can also speak about, for example, the étale side over it, or the smooth side, or even the foliated side, and so on. So maybe I do one of them. Maybe I do just the foliated one because this is what I need. So we can speak about smooth foliation over a diagram. So what is this? This is the category of pairs XFI, where I belongs to big I, and XF is a smooth, or is this diff smooth SI foliation. Okay, and similarly, there is a notion of so whenever you have a topology on for example, the foliated topology, you can induce one on this kind of categories, simply by declaring that the covers are given by families with a fixed index. Okay, so is this clear? And so what is important for us later is that there is so whenever you have a morphism of diagrams, you have also the usual functoriality, like direct image, inverse image, and so on. Okay, and they behave. They have some rich functoriality list of properties. Okay. So here's an example. I mean, I just introduced an example. So I can think about. So we have E bar, theta bar. This is an example. Of diagram of schemes, and you can imagine what it means to, what are the objects of a category like this over such a diagram. Okay, I mean I can say maybe just informally like this. I mean, so if you now look at for example smooth foliation over this guy. This will be some kind of so you can think about it as a category of foliation, but where P1 is rigidified, P1 delta is rigidified in some sense. This would be like yeah. So a variant of this will be the thing that is needed later. Okay. So, somehow what will happen is that there will be some big diagram of schemes which will be used somehow to produce a variant of this P1 delta localization, which somehow can be computed and behaves and give also a model for the spectrum omega. And so this will be a big diagram of schemes. I will not introduce it in one step. So I first introduce a part of it, which is actually responsible of the A1 localization, and I tell you how this is responsible of the A1 localization, and then move to introduce this bigger diagram. All right. Okay, so as I said, I start with the construction. This is actually some kind of, so this will be part of the main diagram of schemes that we'll use later. So I'll denote by Pn. This is the category of finite subset, finite non-empty subsets of N where arrows are inclusion. So this is the category associated to the ordered set of non-empty finite subset of N. Okay, so we have a diagram. We have a diagram of schemes, which I denote by A, Pn, and it's given as follows. So it's given by the functor. From Pn to schemes, and sending a subset I to the scheme AI, which is given as a spectrum, the usual thing, spectrum of K with variables indexed by this set, this finite set I, and then the usual equation. Okay, and so whenever you have an inclusion, you have an inclusion of schemes associated to it. Okay, by declaring that the variable which are not in one of the set goes to 0. Okay, so here's a fact which will be used later, is that this diagram can be used. This diagram can be used to reformulate the Suslin-Volyvodskiy construction. As up to homotopy. So I want to do this properly because it's used later. So first, let's introduce some notation. So I'll be denoting from now and also later in the lectures. So pi will be the map of diagram of schemes like this from A, comma Pn to spectrum K, comma Pn. And so which is given by the projection to the point everywhere. And so for instance, I can speak about pi lower star, pi upper star, and so on. Okay? So yeah. Okay, so now if you have f or k, if k is a complex, say is a complex of presheaves, let's say on a smooth varieties over the field k, and you are interested in, so we have this singular construction. But yeah, by the way, I should say maybe, so this potentially could mean two things. The usual Sustin-Voivodski construction, or the one I introduced today for the object A1. Okay, but it will always mean the first. This will always mean the Sustin-Voivodski construction, except when I have something else. Yeah. Okay. Yeah, I mean, yeah, they do the same thing. So they do the same job, so they should be the same. But this is much nicer as a model. Okay, so I mean, they are quasi-isomorphic, but they are not really the same. Yeah. So yeah, so you have this, and so the claim is that you can recover, again up to homotopy. You can claim you can recover this complex up to homotopy from the direct image by Lauer star of f that you restrict or k that you restrict in the obvious way to the category, I mean to this diagram of scheme. Okay, so if you want, this is an inverse image procedure. You have an inverse image functor, and then you push forward along this map. This will be so this guy here is a complex of presheaves on Pn. No, it's a complex. What is it? It's okay. Maybe it's a diagram. It's a diagram of complexes of presheaves indexed by Pn. Okay, so the claim is that you can use this this thing here to write down a complex which will be isomorphic to that, quasi-isomorphic to that. This is really not so surprising because we have the same ingredient in some sense. Let me tell you how it works. So yeah. So more generally, if you have if A is contravariant functor from Pn to some additive category. So there is an associated complex. So again, it's really in the same spirit of, for example, the complex which is associated to a cubical object or a simplicial object, really the same nature. So that I denote by UA. And it's actually given as a union or maybe colimit over the integers of smaller complexes, which I denote by UNA. And UNA is as follows. So UNA, so it's a complex, and in degree m it's given by I think the direct sum over all subset of 0n of cardinality m plus 1 AI. And there's a differential between them, which are given by the obvious map with some signs. If you really want, I can write it down, but maybe not. All right, so this is the thing, and then we denote by tot. So I denote by tot n by definition, this is a total complex composed with this procedure. And so the claim is that, okay, I can write it down. So this is quasi-isomorphic to tot n applied to pi lower star of f, and to be precise, of k. And if I want to be precise, I would say k restricted to a1 to a p. Okay, so it's in this sense that one recover the Vygotsky construction of those. Okay, so now I can continue and maybe explain the diagram that somehow that is helpful later. Okay, so let's yeah. Okay. Oh, I have a missing page. So I have to remember. Okay, so yeah, so we denote maybe some notation. So I denote by big omega the functor that goes from Pn. So it's actually yeah, it's a presheaf. So let omega be the presheaf. Omega be the presheaf of sets on Pn, given like as follows. So given by so omega I for a finite subset I in Pn in N is a subset of Z1 Durham AI. So differential form on this affine scheme, affine space AI, which are invariant, by translation. Which are invariant. Okay, so for example, if you have coordinates, so this will be just the vector space spanned by dt1 up to dtn. Okay. Right. So this is a presheaf on Pn. So this induces a functor. So from Pn to categories. So we will look at the functor from Pn to categories, which sends I to this weird theta bar with omega I. So we look at this functor. So this is a contravariant functor. And I told you somehow so whenever you have a map of sets, it gives you a functor between these categories. Okay, as I explained before. Okay, so this is the, and then we didn't, so introduce a notation. So I'll denote by theta bar parenthesis omega n. It's a notation, and what is this? This is one can think about it as a integration. So it's called the Grothendieck construction on set to this functor Pn theta bar omega. Okay, so this is this functor, and so so concretely this is the following. So concretely, objects are pairs I alpha, where so I is a finite non-empty subset, from empty, and alpha is this it's an object of theta omega. So it's, if you want, it's a collection of set which is indexed by invariant differential forms. And maybe I should say what are the maps. So what is the map between I alpha and G beta? So this is the same thing. So this is an inclusion. I inside G, and the map alpha to the image of beta by the associated map. So I write it like this. So you have a map from omega G to omega I. You have as an associated functor, so denoted by lower star, and you apply this to beta. So this is some category. I mean, this is, I don't know who introduced this kind of notations, but this is called the Grothendieck construction. So whenever you have a functor from a small category to the category of categories, so a two functor, and then you can associate to this a total thing. So I don't know. It has to do with this notion of fibration between categories. I don't know. It's I don't know. It's some kind of a sum, and you are summing the fibers. I don't know. It's weird. I don't know. Okay, so here's a fact. So so we have a diagram of schemes. So I denote simply by E bar indexed A, and this diagram is indexed by this category theta bar omega n, and so it's given by the functor given sends a pair to E bar alpha AI. Okay, so it's just a product of copies of P1 with some affine space. Okay? We will so introduce some notation. So again, this notation will be used, I think, later. So we have this diagram, theta bar, omega n. There is a natural projection denoted by rho to A1. And I'll keep the same category, so maybe theta bar. And then again, it goes to spec K. This is pi. Again, the same category. Okay, so and whenever I have, for example, a complex of presheaves over I don't know, the foliated maybe site over this diagram, I can push it forward and get a complex of presheaves, which is or a diagram of presheaves indexed by this category. The same way as I did before in the case of A and Pn. Okay, so these are some notations. Now I want to describe a procedure which takes an object indexed by this category and give you a complex again, which is of the same nature as a total complex of a simplicial object or a cubical object and so on, which will be somehow the thing that appears when you do this E-bar localization. Okay, so let's see if maybe also I should say that so we also have a diagram. Foliation, which is E bar A over E omega, which is indexed by the same category. Okay, so so maybe I should say it again. So here's a rough idea of what I want to do now. So given a complex of presheaves on smooth foliation, so we want to compute. Again, it's a variant. It's really not really it's a variant of its P1 delta A1 localization in terms of the direct image along these functors, in terms of pi lower star, rho lower star of the complex. Okay, so this is what I want to explain now. Is this clear? construction. Yeah. Okay, I can do this. So maybe this is a first version of the construction that I want. So start with it. So set V be a set. And as before, I have these objects. Okay, and so I can consider the family and so one has an associated localization functor, which is SG E bar, which is an underfunctor of the category of complexes of presheaves on this. And so this somehow, yeah, it's another function. And then we set SG E bar without the underline to be the global section. So we apply global section, and so you compose global section with this underfunctor. Yeah, and so this is I want to think about this as the analog of the construction which takes a simplicial object in the category of complexes and give you a complex. Okay. All right, and then there is a variant of this, which is the one that we really need. So remember, this depends on a choice of a repetitive order. So we do the following construction. So what we do here, we first choose a repetitive order on the set of on the projective limit over I in Pn of omega i's. So this is already a huge set, and you make it so, yeah. And so once this is fixed, we can do the following. So now given a complex of presheaves on this theta bar omega n, maybe I give a name to this. Okay. So we set dot n gamma theta bar of k. So this is by definition the dot. Did I define dot n? I don't remember. Yeah, I think I did. I introduced this, right? Yeah. So this is you apply this to essentially SGE, which somehow you do it in family in some sense. So this is SGE for one fixed set. Here we have a family of sets, but this still makes sense, and because somehow we choose the order in a compatible way, this makes sense. This actually produces. So this guy produces. So if you apply this to k, this guy here is a presheaf on Pn. Okay, complexes of presheaf on Pn. Okay, so each one here. So this guy takes a complex of presheaf on this category and gives you a single presheaf, a single complex. If you do it in family, then instead of getting a single complex, you would get a complex parameterized by Pn, and then you apply to it again this procedure. it's really not important at all what these kind of things. Just knowing that there is a way which takes a diagram of complexes indexed by this category and give you one complex. Okay? All right? Is there a problem? Is there a problem? You seem Should I continue or? So now I think I have maybe everything to state the new version of the theorem that I wanted to do, that I proved I think last time. So here's a statement. Actually, I think next time I will maybe modify a little bit the statement, but I think for today it's maybe enough to do this. So we start with M. So this will be an psi ft fibrant complex of O delta modules on smooth foliation over K, assumed, so which is also A1 invariant, A1 and P1 delta invariant. So you can think about just the drum complex if you want. This would be essentially an example. Okay. So remember we have associated to M a spectrum. So let M be the associated T spectrum. Which is periodic, so it's given by the same object in every level, maybe up to shift. Okay, so then there exist natural level-wise quasi-isomorphism as follow. So from the total complex n theta bar, so in the previous sense, applied to the direct image pi lower star of the infinite suspension spectrum n on n, and now the important thing is that you don't take you can just take an étale fibrant replacement. Okay, and so it's an isomorphism to the thing that we are interested in. So it's a level-wise quasi-isomorphism. All right. So this is the main theorem, and it's proved really by just, I mean, the same ingredient of the proof I gave last time. So it's just, I mean, so essentially we have somehow produced an artificial context where you can repeat this proof without having to work with CFT topology locally. Okay, that's the idea. Okay, so I think this is all what I had to say for today. Let me check. Yeah, that's it.